A very good evening to each and everyone who are gathered here through online Cisco WebEx and also through Facebook Live. I'm Dr. Deepak, Associate Dean International Affairs, Saveetha School of Engineering. A warm welcome to each and every one of you for SSE E Talk series. This is the 10th SSE E Talk. So far, we have completed successfully 9 SSE E Talks. At the outset, I like to thank our director, madam, for madam's kind support, motivation, guidance in order to organize this event. And I would also like to extend my thanks to our principal sir for his support and guidance. I would also extend my thanks to our vice principal sir for his motivation. Today, we have with us Dr. Sanjay Sharma from University of Plymouth. He is going to address on the topic Marine Autonomous System, Research and Applications. Let me take this opportunity to introduce about him. Dr. Sanjay Sharma is currently working as Associate Professor in Intelligent Autonomous Control Systems in School of Engineering, Computing and Mathematics, University of Plymouth, UK. His area of interest includes marine renewable energy, unmanned marine vehicles, artificial intelligence techniques, engineering design process, engineering industrial control systems. He is the member of Institution of Mechanical Engineers. He has several publications to his credentials. He was external member for many PhD viva at various universities such as University of South Wales, Southampton University, Coventry University, Sheffield University, Plymouth University, and many more. He has supervised more than 10 PhD students. He received several grants and was principal investigator and co-investigator of several ongoing and completed projects. I am very happy to welcome Dr. Sanjay Sharma to deliver his talk. Over to you, Dr. Sanjay Sharma.
Yeah. Thank you very much, Dr. Deepak. Thanks for giving me opportunity to present some of the work I was doing for last 14 years in Plymouth. I just want to give a small background of me so that people know that I'm from India and what I did in India before I come to UK. So I did my bachelor degree in electrical and electronics engineering from IIT Kharagpur. Then I did my master from IIT BHU. And after that, I was selected for engineering service and I was working in Indian Railways for nearly 3-4 years. And then I decided administrative work is not for me. So I came to UK to do my PhD in Sheffield. And after doing my PhD, I moved to Belfast and worked as a research lecturer at Queen's University Belfast. And from 2004, I'm here in Plymouth. So my background is more or less like control system using mostly AI techniques. That was my research work during PhD. And after that, when I joined Plymouth, I started using the same technique, but different area because Plymouth is mostly marine based. So now I'm heading a group called Autonomous Marine System at Plymouth. Most of the talk will be around that. What is my research in marine autonomous system area? Before I start, I just want to give you some of you who have not visited UK. I don't know where the Plymouth is, so you can see in this picture. Plymouth is in the southwest of England. It's not very large populated area, but it's slightly far away from London, but it has got very good coastal line. And it's well connected by many UK cities, either by bus or by train because there are no airport at Plymouth. And you can also go to France and Spain by taking ferry from Plymouth. And Plymouth is considered as a British ocean city. We have one of the biggest, largest aquarium in Plymouth. And then we have the largest collection of Grade 1 listed building in the UK, which is very historical perspective. That building was Royal Navy building. Now it was converted into many cafe and restaurant there. It's a lively place to go there. And it also is a safe city to work, and people are generally happy here because of location, because of south, we have more sunshine and coastal lines, so we have more or less like a tourist area here. And our university is more or less in the middle of city center, so you can go anywhere from the university within walking distance. So everything is accessible from the our campus. So the research group which I'm heading is there are nearly 15 academic staff and researchers at the moment, and most of the people are expertise in doing something related to AI techniques, optimization. They are using advanced control system techniques, multi-sensor data fusion, integrated navigation system, and mostly application of AI techniques in the design of navigation guidance control of autonomous vehicle. But we are also working in some other marine-related devices like wave energy devices, marine propulsion systems. So this is more or less very old picture, but it's very difficult to get everyone on board at the same time. So this is the picture you can see on our website as well. So these are some of the people, academic and researchers in this picture. So most of the time we are using AI techniques for designing autopilot for autonomous marine vehicles. We have many. We have underwater vehicle, we have surface vehicle, and we have glider, we have some other kayak type vehicle as well. And since we are doing all the time autonomous, so there are many sensors which will be attached to the vehicle. So we are doing sensor fusion and filtering techniques to get the optimal estimate from the sensor. And this vehicle sometimes goes around the shore and trolley motor and blade can strike with the stone and it can break. So we have some fault diagnostic method to identify the fault going on inside water. And this vehicle can be used for many purposes. One of the PhD is completed. He has used this vehicle collecting the data for subsea cable localization. Similarly, another PhD he has completed on how to land a quadcopter on this vehicle. So he designed some deep reinforcement technique and integrated marine observation system for this vehicle. Another PhD guy, he was from IIT Chennai, and he designed a swarm optimization and optimal path planning of the vehicle when more than one vehicle are coordinating together and doing some pre-planned configuration and moving in a path. And some of our colleagues are also doing many research in communication, because communication underwater is very challenging area. And we have sound communication, acoustic one, but acoustic communication is very power prone. So there is recently some research going on in many commercial company as well as academic to use the radio frequency communication underwater. So C is trying to develop some protocol where we can get some data, not in a continuous mode, but some good information from the underwater vehicle by using radio frequency communication. And the advantage will be that the equipment will be smaller, the battery power required will be less, and it can give data for longer duration. So the large advantage of using radio frequency communication for underwater communication. So our journey started in 2001. Uh, First, we developed the underwater vehicle, it's called autonomous underwater vehicle, which are called Hammerhead. And this project was with Cranfield and Southampton, and we were assigned to develop navigational system for this vehicle using multi-sensor data fusion and fuzzy logic Kalman filter. And this was originally a deep mobile target, means you could say torpedo, and then we converted this one as a autonomous underwater vehicle. If you can see here, this vehicle has got many compartments, having control system, GPS, different type of sensor, battery, computers, and the compass. And then the back part is the ejection part. When it will be ejected, the vehicle will come on the surface in case of emergency. So how it works, the vehicle takes its position from GPS when you're on the surface of water, and then it dives underwater. And the purpose of the vehicle where the current field was designing a laser type system where they can track the cable by laser beam and maintain a constant height from the cable. So it goes down and track along the cable, and then the heading and other things are estimated on the basis of compass and IOMU. And after some time, this vehicle comes out and again takes its position from the GPS. And if there is some error in the estimation, it will correct itself and then again dive down and keep on doing the same operation. So this is the purpose. So we were involved in designing only multi-sensor data fusion for optimal estimate and sensor redundancy. If the sensor goes fault, the estimation will still continue to give you the correct reading. So this is some of the experiment we did in the lab. And this is one of the experiment where we are tracking the cable by using this type system. So how the multi-sensor data fusion work? Maybe I will move this one here. So there are many sensors in the vehicle which are doing the complementary work. So, and then we use some AI-based techniques here, fuzzy logic-based techniques, where we combine the sensor reading and get the optimal estimate by using Kalman filter. And that optimal estimate can be your heading or can be position. So you give that feedback to your control system where you have already designed some predefined path. And if there is some error, then the controller try to bring back your vehicle in the predefined path. So it's very important because if anyone know about the Kalman filter is mostly diverse very fast because we require very exact process noise covariance and measurement noise covariance matrix. So proper process noise covariance matrix is Q, which you can get it by designing a good model. So mostly models are correct, but the measurement are always noisy. So we have designed an adaptive Kalman filter by using fuzzy logic, where we can tune the R matrix to avoid the Kalman filter to get diverse. And that works very well when you see the result. And otherwise, it's difficult to work with the Kalman filter in real application. So compass and the IMU is always noisy, and noise increases with time for the compass, and it's nearly time square. And so you cannot take this reading directly as a reading from the sensor and design something. So we have to take out the noise, and the best thing is to filter out the noise. And most of the time, designing in autopilot, whether in a marine area or in aerospace area, people are using Kalman filter. So we have also used Kalman filter to get rid of the noise from the sensor reading, so that we can design something on the basis of noise-free data. Otherwise, we will be taking action all the time unnecessarily. So you can see the picture here. Here, the estimation of the sensor is based on Kalman filter, which is fuzzy logic tune. You can see the Kalman filter is able to take out most of the noise from the sensor and is able to estimate the same as the real estimate. So the red line, which is the estimated line to Kalman filter, is same as a blue line, which could have been the actual output, actual position of the vehicle. This is a small video where we have used that navigational techniques to estimate the heading angle of the underwater vehicle. So after some time, it will go inside water, so we will not be able to see anything. So this is the vehicle we tested in the lake, which is near to Plymouth. It's called Rodford Lake. Mostly we use that lake for testing anything in a real. And most of the time we will be working on simulation because we already have collected data for many testing, and we have already represented the vehicle on computer. So many things are designed offline and tested in simulation before we go for real testing, because it's very costly and require huge manpower and need to book a space as well. So after underwater vehicle, we find many problems because we are lucky enough not to lose the vehicle. So we thought, okay, it's better to shift some other area. Otherwise, we will not be continuing research in the same area. If you lose the vehicle, then all research will be stopped. So we try to build a surface vehicle, and that's why the 2004 we got funding, where we have built a surface vehicle called the Springer, which you can see here. It's a catamaran type vehicle, and that the main purpose was to do all the navigational guidance and control and develop it for Springer and test it. So it was more or less a testing bed for testing many sensor techniques, autopilot techniques, and it can be used for any data collection like a hydrographic data collection or environmental data collection. So we have done many autopilot design on this Springer vehicle using many different techniques like autopilot system based on genetic algorithm, model predictive control, fuzzy logic controller, and we have also used the different type of multi-sensor fusion technique, fault tolerant based on data fusion using fuzzy logic. And there's all these people, there is one people completing one PhD in every area. And once we have done it, then we have taken the trials in the Rodford Lake to validate that the techniques which we have tested in simulation is actually working. So this vehicle is nearly 600 kilograms in air, 4 by 2.3 meter. And this has got two trolley motors at the back. And then the direction heading of the vehicle is based on differential thrust produced by the two trolley motors. And it can achieve nearly 8 knots of maximum speed. And it has got two pelicases on top, and one pelicase is mostly dedicated to sensor, another pelicase is dedicated to control navigation system. But this was old, now we have changed it because previously the PC was nearly very big decks of PC, but now we are using the battery operated low power laptop inside pelicase. So how it works means it has got many sensors like compass, IMU, GPS, visual sensor as well, which combine together to give a navigational information of the vehicle, which goes to the guidance system where we guide the system and provide the information to the control system, and the control system takes action to bring the vehicle back in a track or keep the vehicle on track. So this is one of the autopilot we designed for vehicle using LQG. So LQG is the optimal control, which is for linear quadratic Gaussian type control. So where we are getting the estimate of the vehicle position by using Kalman filter, which you have seen it before, where we are tuning the parameters of Kalman filter by fuzzy logic. And that position is compared with the predefined trajectory. If there is error, then LQG controller try to optimally control the USB to bring back the vehicle position in a fasted manner with a less amount of energy. Because most of the autonomous system, we try to design optimal controllers so that we can make a constraint on power, because power is the main thing. So our Springer vehicle can run up to 8 hours on a battery if everything is okay. Otherwise, we just design everything on the basis of 4 hours. So optimal controller and optimal action is very important for any autonomous vehicle. So most of the time we are trying to design an optimal autopilot. It takes less amount of energy and give faster response. So one of the PhD completed on a multi-sensor data fusion with fault tolerance, where many sensors are combined together by fuzzy logic, and then the global estimation of the sensor is decided by the fuzzy logic as well. And you can see the result here. There are three different type of compass. Every compass is giving the head angle, and after 300 seconds, the permanent fault was developed in one of the compass, but still the estimation of the heading angle is not deteriorated. So that's the beauty of the multi-sensor data fusion, because if one sensor goes out of nature, then still your estimation will be correct. And we have also tested if all the three sensors has gone out for momentarily, maybe for 50 seconds, still your estimation was correct because it was based on calculation, not based on the actual data for some time. But after 50 seconds, it deviates. So intermittent sensor fault, this type of technique can always take care of. And that's very important for autonomous system, because intermittently you can lose power, you can lose the signal, mostly in the GPS case. And we don't want to get vehicle confused if there are no signals. So we always estimate well in advance, and even the signal is lost, the estimation still works. And it deteriorates with time, but it still works. So how it works? So it takes the GPS fixes from the satellite and then determine the position, and then we already predefine the position, and then the controller action is taken so that the vehicle moves in a predefined path. But what will happen if there is no GPS signal? Because GPS signal intermittent is okay, but if it's totally lost and a weak or maybe jam because your vehicle may be near to enemy territory where the signal will not be available. In that case, we wanted to design some robust navigation control and guidance system for the Springer vehicle. So that was the reason, because GPS signals are very weak sometimes, they can be easily jammed, and signal can be lost if the vehicle is going under the bridge or maybe going near to the tree areas, so the signal will be lost. So this is not a very robust system for any vehicle autopilot system. So that's why we started another project in 2007, where we wanted to design a slightly intelligent visual type autopilot for this Springer system. And the idea is similar, like if you are going in any place many times, then if you are left there after some time, you can easily navigate because you know left hand side is this, right hand side is this, and front was church, so I know the area, so I can just navigate easily in that area without any information. So similar techniques are used here. We collected the data of the territory where we wanted to move in a different season when the features are changing. So we collected all the features in different months, and then we try to build a map based on that feature. So there were technique used which can reduce the dimension of the feature, because this should be real time, because image processing is very power consuming. So the technique should be used very intelligently so that the processing is fast. So we use some feature reduction as well as different type of techniques where we can optimize the feature. And then we created the scene which described the more or less scenario of the vehicle where it is going to move, and then build a map for the vehicle. And if at any time the GPS signal is lost, because this runs in parallel in the vehicle, then vehicle will not be lost and keep on moving on the basis of visual features. So this one we tested, not 100% tested for everything, but tested a bit and it was working. but it could have been working better if you have more power, processing power, computer on our vehicle. But the concept was working. We tested it in our campus just by moving the camera and using this technique. So it creates the descriptor map and everything is okay. But real time, we have not tested much apart from one test. Then we also thought all the time we are designing Kalman filter, and the Kalman filter, if you know, is very, very necessary in autonomous system because it improves the accuracy of the sensor, remove the noise, and if some noise sensor are faulty, you can optimally estimate. So it can also provide you sensor redundancy. The problem with the Kalman filter is point estimation. So you have to know the exact model of the system. But over the time, the model can deteriorate. And then your Kalman filter will start diverging. And that's the problem all the time in the real system. So there was technique which is called interval Kalman filter technique. So where you can estimate in the interval rather than a point estimation. So this interval Kalman filter provides you estimates within some interval, and that interval you can create by changing because you think, okay, something is not known exactly, but you know that it will lie within that range. So you can just, rather than calculating a point estimation by knowing exactly, you can just get a estimation within a boundary. So you have the probability of getting estimation within a boundary. So this is the estimation within a boundary between the green. The problem is that we cannot design anything on the boundary. So we have to get the estimation, point estimation to work for our algorithm. So what he did, he used the neural network and he trained the neural network which provide the point estimation on the basis of boundary estimation. And that point estimation was same as you could have done by using only Kalman filter, which give the point estimation. So now we have the provision where we can take a bit of error in our process and where you can, rather than estimating a point estimation, we can estimate in the boundary and use the neural network to get the point estimation, which we can use for our navigational process. And that we use and we tested and it works. And there's one PhD on this. So another PhD, because we did many autopilot, but we have not taken care of any dynamic change behavior of the vehicle. And this can occur because of you have suddenly change in the payload and maybe environmental conditions are suddenly changed. So the dynamic of the vehicle will change. And then to take into account, we have designed adaptive autopilot. So we have combine the online closed loop identification with model predictive controller, which is also an optimal controller, to see the effect of change in dynamics of the vehicle, whether this controller is going to work or not. And the idea came from because US Navy tested Rafale spike missiles from unmanned surface vehicle. And once you fire missiles, there is a sudden change in the mass of the vehicle. And this sudden change in the mass can deviate your vehicle from predefined path. So you may be operating near to enemy border and suddenly a fire missiles and your vehicle also deviated and gone inside enemy territory. And in that case, you lost your vehicle. So we wanted to test what will happen if you suddenly fire a missiles or suddenly change the mass of the vehicle. So obviously we cannot fire missiles from our vehicle, Springer vehicle. So what we did, we put 2 jerry cans full of water, nearly 100 kilograms, and after some time we pull it at the same time by using the rib, and then collected the data and then seen what is the effect of the model predictive control, adaptive one and without adaptive one. So here you can see this is the time when we pull the both masses from the vehicle. So you can see the red one is the vehicle path. So you can see the vehicle started deviating from the desired path and is not able to come back to the desired path. So there is so much deviation, so it's all totally moving in a different path now. And this may be an meter territory as well. But in the case of adaptive model predictive control, you can see even we take out the mass, suddenly at this point, the vehicle is still following the desired trajectory. So this was very great advantage of using adaptive autopilot for Springer, which I have not done before. And that can be used for many purposes. So similarly, we have collected many data from our experiment, and we started designing different type of autopilot in simulation just to see whether it works or not. So I was working in Belfast where I was designing local control network for chemical plant, because local control network is based on the local operating region, which is well defined in a chemical industry. So you can design a controller for local operating region, and then you combine it together. So if the operating region change, one controller shift to another controller smoothly by using some weighting function. So it's combined, all the linear controller are combined and weighted through some weighting function. So I was just thinking, okay, let's see whether I can apply the similar idea for designing autopilot here or not. So since we don't know the operating region of the Springer, we use the genetic algorithm where you can find the optimized number of local controller and all the parameters associated with the weighting function. And then we designed autopilot and tested it for change in step heading angle, and also tested it for the random change in heading angle. So in both cases, you can see the vehicle was able to track the desired path perfectly. Then we already designed a model predictive controller we wanted to test, because there is a nonlinearity in the overall system, because system operate in the environment and interact with the environment, so overall system become nonlinear. So we wanted to design some nonlinear multi-predictive controller to get a slightly optimal control action, and that we also did by using genetic algorithms. So we use genetic algorithm to design a nonlinear model predictive control autopilot for Springer. And if you can see the result here, the controller is able to keep the vehicle on track. And this was tested in a slightly harsh environment. So that's why the nonlinear autopilot is slightly important if you are testing the vehicle in slightly harsh environment where you don't know the dynamics will be linear or non-linear. So you take care of that. So all these things are tested in the same route for lag. So you can see here the vehicles are moving and tracking the predefined trajectory. And this was done on the request of our hydrographical people, because they wanted to track the path in this lake, which was submerged with water 20 years before. So they have the data 20 years before, and they know where the road was going. This was village, and they wanted to see after 20 years how the things had changed. So they have collected the data using side scan sonar. So we have collected the data for them and given them to analyze it, and they published some paper on that. So that this vehicle was used to get the autonomous data in a predefined path in the lake, which was provided, coordinate was provided by hydrological people. I'm also associated with many different type of projects which are related to marine area, but not totally autonomous vehicle. So one of my PhD completed, he designed a navigational system for biometric type robotic fish. So doing CFD and simulation and all these things. And one of the another PhD, he completed his PhD designing a subsea cable tracking, I mean, estimating the burial position and the depth of the subsea cable using particle filter estimation. And one of the PhD has completed by using deep reinforcement learning how to land quadcopter on autonomous surface vehicle. Another PhD has completed where he designed a cooperative path planning for swarm of USV, and he has shown his work well for more than 3 and 4 USV working in cooperation. You can see the results later. Another PhD is completed where he designed a fault diagnostic system of the blade, thruster motor blade for our vehicle. So what was the problem? Whenever we operate the vehicle in the lake and we have the rib going along with the vehicle, we are also there near to the vehicle. So we listen many noise. Sometimes we are afraid the vehicle might have a strike with a stone and go near to the shore. So we always go and kill the switch and bring the vehicle back and check it and then again put it back. So it's a huge amount of time lost, nearly 3-4 hour loss. So we wanted to devise some techniques where we can know that how much percentage of the blade is broken. Because if it's broken less than half, we can still continue the operation without losing much efficiency. But if it's broken half and more than half, then we have to stop the operation. So we wanted to design some automatic fault classification system. So one PhD completed on that. So he has collected data by using current and the vibration of the trolley motor, and then he wanted to get the best feature from the data, so he used wavelet transformation to get the feature from the data. There were many features, so he wanted to get reduced features, so he used the orthogonal fuzzy neighborhood discriminative analysis, which is the technique mostly used for medical data because they have huge amount of data, but he used for this purpose as well. It works. And once the optimal feature is obtained, he tried to classify the fault by using neural network. So when you see the graph here, you can see it's more or less like a linear graph. So by seeing the output from the graph, we can easily say whether the blade is broken 50%, less than 10%, 25%, or whatever, and then we can take the decision whether to continue operation or not. So this was very useful thing for us, and still we using this technique. So the guy who was trying to develop the subsea cable tracking. So this we developed because we are approached by one company who was using diver to track the subsea cable, which is buried sometime before, and there might some fault has been developed. And they are getting an error of 3 meter, and 3 meter underwater error is too much because you are digging the area where the cable is not there, and digging underwater is not very efficient. So they wanted to develop some techniques where they can reduce this error so that they can exactly know where the cable is, because over the time the cable location shifted. So they know the cable was laid here, but it's not there because it might have been shifted by current, might have been shifted by ship anchor and all these things. So they wanted to develop some techniques where they can do it correctly. And so what they are doing before, they are sending some diver with magnetic sensor. When the diver goes down, they send some signal through this cable, and the diver pick up the signal uh, when it's near to the cable, and then depending upon the diver, because he can pick the good signal, he can pick the low signal, low quality signal slightly far away, then he bubbles out that he picked the signal, and someone is on the ship will put the marker on the map that the signal is coming from there. The difficulty is that everything depends on the diver. If the diver is sending wrong quality signal and indicating that he is getting the beep, good beep, then you are tracking the cable in a wrong direction. Other problem is that when he's bubbling out, the bubble can also divert. It's not coming perpendicular to the place where he is bubbling out. So this creates problem, and the diver is very costly. You cannot put diver for long time as well, so you not be able to collect enough information of the cable, and the distance of the cable will not be able to cover it. So this was the problem, and they were getting many work contracted all over the world, and they wanted to do something intelligent. So they came to us. So we suggested some Kalman filter technique. So, but when the PhD started, he suddenly realized the Kalman filter is not going to work in this case. It diverges all the time. So he devised a techniques using particle filter estimation techniques. And the idea was that the company told us that they can get some signal on top, but they are not sure where the signal is coming from. So the signal, they receive it when they travel perpendicular to the cable. So we say, okay, let's obtain that signal and try to estimate on the basis of that signal. So we have used that signal and use the particle filter estimation techniques, and we reduce the error from 3 meter to 0.3 meter. And now this PhD person has opened his own company, and he is traveling all over the world because there's so much demand, because it's very costly affair. So he is working with the same company, and sometimes he is also doing consultancy separately. So the idea is to move the vehicle along the cable, because you know the cable is laid like that, and then collect the data in the near region, and then use particle filter estimation to estimate the location as well as depth of the cable, and give that information to the company, who can go and rectify or maybe take out the cable and rectify the fault. So another person designed cooperative motion planning using many different type of optimal path planning, A star and other technique, and where he wanted to move the vehicle in swarm from one position to another position in a less amount of time, so that it should be have very optimal time and optimal energy consumption. So this is also, there are many paper in ocean engineering about this one, and he compared the result with the existing technology the UCL people are using, and we have shown we have slightly better than them, and that's why we publish in ocean engineering. The results were published in ocean engineering. And this is the intelligence navigation integrated marine observation system, where you can see the simulation is done where quadcopter is following different path and landing on the surface vehicle. So first we wanted to collect the data by doing actual experiment, but we could not get permission to fly quadcopter in the marine area. So any other area, because at that time the quadcopter means you have to go through many channels. It takes a long time to get the permission. But we wanted to complete something, so we did a small experiment, many experiment in our building, where we have collected the data for all possible scenario which the quadcopter can find in the marine vehicle. So we collected the data by using many obstruction. We collected the data with many different type of marker, where the marker can fade away in the water, and marker can also also change the positions, orientation. So different type of data is collected, and that's the main thing in a deep reinforcement learning, that you have to collect the data in all possible scenarios, and that takes huge amount of time. And after that, you train it so that the quadcopter can land peacefully on the marker. So he tried to land it by using an inclined landing on the marker. The problem is that when the quadcopter comes near to the marker become invisible after some time, because it comes so near, so you're not able to land on the marker. So what he designed the double deep reinforcement learning. So one deep reinforcement learning was flying the quadcopter in horizontal direction until it see the marker and then lock with the marker. And then another deep reinforcement learning was done to bring back the quadcopter on the marker in a vertical direction. And that works really well for all situations. But it's taken a long time to train and simulate the things. But yes, he's working as a postdoc now in uh, Lincoln University. So we also have sailing boat in our research area, and we designed the sailing boat. One of the PhD completed, one postdoc as well. And the advantage of sailing boat is that it's a cost-effective, energy self-sufficient, because we are also planning to put the solar panel on that. So this can be used for long duration civilian or military mission, whatever you want. So we have recently got one funding for the PhD, which we'll describe later. We'll be starting on the sailing boat. This course, because we have expert in marine and robotic autonomy. There are many people working in robotic autonomy. We are working in marine autonomy. So we have expert in this area. So we designed a new program called MSc Autonomous System, which is started from this year, where the people will learn about artificial intelligence techniques, navigation and guidance techniques, control sensor fusion, machine learning, security, communication, networking, data management. Because all these techniques are very important if you want to run anything autonomously. So all these things will be covered in this MSc program. So if someone is interested, they can see the details in our website, which is MSc Autonomous System. They have the course details, key features, entry requirements, how to apply and everything. All details are here. So this, you can see it. I'm also working with another research group called Plymouth Ocean Forecasting Center, where we are applying the research to deliver an ocean forecasting model for our customer. And we are working with the UAE Navy, where we are designing an ocean forecasting model for UAE Navy. It's slightly commercial, uh, confidential thing, so I'm not going into detail what we are doing there, but we are working with that. UA Navy, we're designing ocean forecasting model for them, for their military use. And since Plymouth is more or less marine based, so we have a cluster in area, because we have Thales company, which is a big company in marine autonomy, and many small company, which you can see the logo at the right hand side. So we have created a cluster which is called FAST cluster, which is a future autonomy at sea technology. So this is based at Plymouth, which more or less bring all the businesses in autonomy as well as academics, and we have formed a partnership where we help each other either doing research or grant or any other things we want to do in the future in a marine autonomy area. So we have some vehicle apart from the vehicle we have already seen. We have some extra vehicle as well. So we have some low cost the hydrographic vehicle which can be used for collecting data. So this one. And then we recently bought a new underwater unmanned surface vehicle from European Regional Development Funds, and that is to support a small business in Plymouth to use this vehicle as a test bed. So they can use this vehicle for whatever purpose they want to use it. So this vehicle is diesel operated, where battery is also there, and it's nearly 1 ton, and it can be configured for many things. You can put any sensor you like, you can use any software you like, you can control it by using internet, you can control it by using ROS, you can control it using by MATLAB. So there's many possibility of live view, many possibility of interfacing with this vehicle, and this vehicle will be available to all businesses in Plymouth for testing. Either they want to test their sensor or some technology or whatever. So we have this vehicle, and after 21 next year, this vehicle will be coming to our group, which will be solely used for research. But for the time being, this vehicle will be used by commercial people only, and we'll be supporting them. So you may be knowing that there's a Mayflower 2020 is a 400th anniversary of the people who went from Plymouth, UK to Plymouth, US. So we try to commemorate that event by sending an autonomous ship from here to US. and that's we are planning to do some things on 6th of September 2020. It was going to be a big event, but because of COVID-19, it's going to be a small event and maybe local wise. And when the things are settled down, then we'll do the actual uh, journey from here to US. But for the time being, we'll start something. So this vehicle has been built in Poland, now is back in UK, and MSUPS Limited in Plymouth is leading this project. And we are using many different type of sensor, providing them and helping them to use our technology for designing many things. So we are working with them to complete this project. We also have very active cybersecurity group here who are working in a maritime area because everything is started working autonomously now. You can see the autonomous big ship like for transportation. Norway has already started testing, but the problem with the autonomous system will be when it's a very expensive ship moving without any pilot and without any human, then it maybe somebody can hack it, and rather than going to one place, it can divert to another place. So cybersecurity is the big area in the maritime, and we have the many people working in this area, and we are also collaborating with them.